Hello everybody, welcome back. Today we're taking a look at the Leetcode problem number 11, container with most water. So this problem is actually pretty straightforward. We're given an array of heights, or height, declared right here, and using this array of heights, we're expected to find the largest area that we can form with two walls, to essentially form a container that can hold the most amount of water. So if we take a look at example 1 right here, you can see that our height input is an array of this. So our heights are 1, 8, 6, 2, 5, 4, 8, 3, 7. And so using these heights, we want to find the area which can hold the most water. And just by looking at it, you can see that our max area is 49 because our container caps out at 7 right here, and the width is 1, 2, 3, 4, 5, 6, 7. So 7 by 7 equals 49, which makes sense because that tracks with what our output is. So that's basically what the problem expects us to do. We just need to find the maximum area. So now let's dive into a brute force solution. Let's think of a way of how we can find the maximum area in an array of given heights. So let me just erase this real quick. So as far as a brute force solution goes, the first thing that comes to my mind is just trying out every possible combination and then tracking the max area that way. And then after everything's said and done, we can just return the largest area that we've calculated so far. And so in order for us to actually calculate every area, we need to be able to track two different heights at the same time so then we can calculate the area. So that means we're going to start with 2 pointers at different indexes. So we can start with a pointer at the first index here and the second index. And so now with our pointers at different locations, we can try to calculate the area between these two heights. So just to have a quick visual reference, imagine this area was filled with water. If we have any more water, then it will spill over, which obviously we don't want. So the maximum area that we can get between these two heights is just 1. And the important thing to take away from this is that the reason why it's 1 is because we are bottlenecked by this height right here. Remember, it doesn't matter if this wall right here is 8 or 9 or 10 or a million, because if we were to fill water here, it will only cap out at 1 because of the smallest wall right here. So that pretty much tells us whenever we're calculating the area between two heights, we first must determine the minimum between the two heights, and then we can multiply that with the width between those two heights. By doing that, we can accurately get the max area between those two walls. Alright, so that's the first calculation. So now we can move our right pointer over by 1 and do another calculation. So I'll get rid of this real quick. So now our right pointer moves right here. And again, just to visualize, imagine if this was all filled with water. Again, the left pointer here with the height of 1 is our bottleneck. So if we were to fill this area between these two walls with water, then it would still have a height of 1, but our width is now greater, so we have a width of 2. So 2 times 1 is 2. So hopefully that's all making sense. Remember, we always have to be conscious of whichever pointer is going to have our shorter wall. Because if we fill that space between the two pointers, the water will rise to the height of the shortest wall. So let me just fast forward a bit through this brute force example so I can just show you how the rest of this would look. This right pointer will continue exploring to the right, and because our leftmost pointer has a height of 1, the max area that we calculate right here will be 1 times whatever the width is. So this pool of water will just increasingly get bigger until we hit the end. Once this right pointer reaches the end, then we start another iteration, which would involve incrementing our left pointer up by 1 and then repeating the process all over again. So now we're beginning our second iteration. So we moved our left pointer up right here, which has a height of 8. And our right pointer is now here, which has a height of 6. So now this container can actually hold more. As you can see, imagine we just fill this with water. So we'll have a width of 1 times our height of 6. Because our right pointer has a height of 6 versus our left pointer, which has a height of 8, we're bottlenecked by whatever the shortest height is, so it'll be 6 times 1. So our max area here is just 6. So that's pretty much the general process we're going to follow. So let's just fast track to the part where we find the optimal solution. So eventually our right pointer will reach the very end, like so. And so when we calculate the area here, we first must determine the minimum height. So we're dealing with 8 or 7. We're going to go with 7 since that's smaller. So it's going to be a height of 7 times whatever our width is. So our width is 1, 2, 3, 4, 5, 6, 7. which obviously the problem is already highlighted right here. But again, 7 times 7 is 49, so that's how we get our optimal solution with the brute force. Now, while this approach is straightforward, it's also not very efficient, and I doubt any interviewer would accept this answer, as it has a runtime of O of n squared. Generally speaking, most algorithms that have a runtime of O of n squared can be improved upon, which is the case here. And we can actually get the runtime down to O of n time by leveraging the two-pointer pattern. Now, you might be thinking, the brute force uses two pointers, so how is using the exact same strategy going to get us a better runtime? Well, it's all about how you use those pointers. So instead of using two pointers to do a linear scan of the array to find every single combination, if we use the pointers more strategically, we can actually cut down on a lot of repeat work. And so this two-pointer pattern is very common among problems that either use arrays, linked lists, and strings, because the two pointers work very well to scan the linear input that arrays, linked lists, or strings offer us. Generally, if you have to find all possible combinations of something in one of these data structures, and your initial runtime is O of n squared, then that's a clear indicator to leverage the two pointers pattern. It's also a clear giveaway if you use two pointers in the brute force solution, like we did with this problem. Which, by the way, if you're interested in reading about more coding patterns like this one, then check out my article linked in the description below, where I go over the 15 most common coding patterns encountered in interviews. In any case, this pattern gives us a path forward. So how can we improve our runtime from O of n squared to O of n? Like I said, our runtime comes from the repeat work we're doing, because we're exhausting every possible array combination in our list. So what can we do? Instead of having one pointer remain stationary while the other explores all of their options, what if we put our pointers on both ends? Like so. Doing this allows us to start with a maximum width between our two pointers. From here, we can incrementally move our pointers inward, computing the area and keeping a running total of the largest area encountered so far. With this technique, we're still looking at all the possible areas, but without any of the repeat work. In other words, we're working smarter, not harder. And that's really the goal that we're striving for when working with coding patterns. Remember, when we have two walls, the bottleneck is going to be the shorter one, so we can calculate the area by finding the height of the shortest wall, then multiplying that by the width. We can keep track of this result and then move one of our pointers inward. The pointer we must move will be the pointer at the shortest wall. So again, let's go through example 1 with this new approach. So we have our two pointers here, one with a height of 1 and the other with a height of 7. So the shortest height is going to be the left pointer with a height of 1, which means our max area will be 1 times our width, which in this case is 8. So that leaves us with a max area of 8. So after calculating the area, we have to move a pointer inward. In this case, we'll be moving the left one inward because the left pointer is shorter than the right pointer. So we'll move this pointer over by 1. So the left pointer will now move to index 1, which as you can see has a height of 8. Now I've already explained the reasoning behind this because it's outlined right here, which means we've already found our max area. So remember, our width of 7 times the shortest height between 8 and 7, which is 7, so 7 times 7 is 49, which is much greater than the 8 we just calculated. Now, although we know that 49 is the max area for this problem, we don't know that yet. We still have to explore the entire heights array before we can determine definitively that 49 is the max area. And so again, following through with the example, between the left pointer, which has a height of 8, and the right pointer with a height of 7, since the right pointer is shorter, we must move this one inward, which we will do. So now our minimum height here between the two is going to be 3. So 3 times 1, 2, 3, 4, 5, 6, which is 18. Since right is shorter, we'll move that inwards. Now here's where an interesting edge case crops up. As you can see, our left pointer has a height of 8, but so does our right. So what do we do in a case like this? Well, it actually doesn't matter which one we increment inwards, either left or right. In the event of an edge case like this, I guess you could just code it in a way to where the left pointer will move inward should the left and right have the same height. But it's up to you. In our case, we will just move the left pointer inward. And then the problem continues as normal. So we have a height of 6 versus a height of 8. So it'll be 6 times 1, 2, 3, 4. So we'll have a max area of 24. Since left is smaller, it'll move inward. So it moves over. So now we're dealing with a minimum height of 2 times 1, 2, 3. So this will be an area of 6. Again, we move the left pointer over, like so. And then just to fast track this, after we're done with this calculation, the pointer will move to the right, we'll do this calculation, and then finally the left pointer will move over to the right, where it will then overlap with the right pointer. Once the 2 pointers overlap, that is our exit condition. We can break out of this loop and then return our max area, which at this point is still calculated to be 49. Now, the runtime for this will be, like I mentioned earlier, O of n, because we're doing this whole thing in one pass. And then the space is going to be O of 1, since we don't use any extra space. So overall, a pretty significant improvement from our brute force solution. Alright, so hopefully all that made sense. Now let's dive into the code. Alright, so the first thing we want to do is initialize our left and right pointers. So we can do that simply by declaring left and right equals 0 and length of our height input -1. This will set left and right at the beginning and end of the list, respectively. Then we need to declare our variable max area, which will just keep track of the running total of our max area. We'll set it initially to 0. So now that we have our variables out of the way, now we have to enter our loop. So remember, as long as the left pointer does not overlap with the right pointer, we can continue iterating and calculating the area within our height input. So we can simply just declare a while loop of left less than right. So as long as they don't overlap, we can continue with the logic below. So the first thing we want to do is calculate the width, which will just be right minus left. Once we have width, we also want to get the height. So height will just be declared as h, because our input is already named height. And remember, we want to get the minimum between our left and right pointer. So it'll just be min of height left and height right. So once we've determined our bottleneck, then next we can just simply calculate our max area. So we can say max area equals the max of either max area or width times height, or h in this case. So again, here we just calculate the area of the current container, or we update the maximum area if needed. After we calculate our max area is when we decide whether to move the left pointer inward or the right pointer inward. So we can just say if height left is less than height right, then we will move the left pointer to the right, or inwards. So that'll look like left plus equals 1. And if that is not the case, we can just simply say else right minus equal 1. Because since the right is on the other end of the height array, we have to decrement it to get it to move leftward. And that's pretty much it. We can just continue this logic until left and right overlap, after which we break out, and then we simply return our max area. So that's going to do it for the container with most water problem. I hope you guys learned a lot. And if you like this video, then I encourage you to check out my playlist where I have other videos like this, where I solve other Leetcode problems, as well as teach you helpful patterns along the way. So that being said, I'll see you guys in the next one.